Last wonderful day. I'm going to start with a video. I don't mind admitting I'm a big Simpsons fan. I wasn't originally, but I am now. And I always thought of this quote as we were going through this class, and so, well, here we go, because I never ended up showing it to you.
This is becoming very obsessive. This morning, I got trying to dissect your own coat.
I know. This perpetual motion machine she made today is a joke. Just keep going faster and faster. Each up, get in here. And this must be okay to launch a thermal.
Oh, I love it. I'm doing it again.
This morning, I got trying to dissect your own coat.
I know. This perpetual motion machine she made today is a joke. Just keep going faster and faster. Each up, get in here. And this must be okay to launch a thermal.
Oh, good times. So what's wrong with a perpetual motion machine? Why doesn't it exist? Why can't you create it? Can't create energy. Yeah, a perpetual motion machine, the gist is it's like you're getting energy out without putting energy in. Yeah, no, you at least have to conserve energy. Which law of thermodynamics is that? First, right. And then he says in this house, oh, we'll obey the laws of thermodynamics. The second one says, even if you could convert 100% to here, I mean, you're keeping it equal. You're not creating energy out of nothing. It's not going to be 100% efficient. So there's no way the thing would get faster and faster and faster on its own. All right. I'm going to start with doing a thermodynamics demo. It'll help us review a little bit, and I wanted to make a treat for you. So we're going to make ice cream right here, right now. What are the ingredients of ice cream? Sugar. This is my favorite ingredient of ice cream. All right. That should be good, right? What else? Cream. Here, Brandon, you want to help me pour these in? If you'd be so kind. What else is in ice cream? Vanilla. Go ahead. Let's see. There's a tablespoon. Maybe another one. And we want it to taste good. Okay. What else? Eggs are in some recipes, yes. I'm choosing not to in this one, so we didn't have to worry about that. Ice is a fallacy. You use ice to make ice cream, but I don't want to be eating it. What does the ice do? Yeah, it freezes it. It's going to transfer this is warmer than the ice, so heat will flow out of this and into the ice. So it's used to cool the mixture. What else? Salt. Like the ice. I don't want to eat salt in my ice cream. You don't either. What's the salt for? Thank you, Brandon. It lowers the freezing temperature of ice, so the ice can get a little colder before it transitions that phase change from melting or freezing. It's the same temperature. So you can have your ice be colder, and it helps make it go faster. So the ice and the salt you don't want in it, but you can use them to chill it. I'm not going to use either of those. I'm going to use liquid nitrogen to cool it down. So that's how I'll do it. But we're still missing a big ingredient. Pineapples, yes, you can flavor it up however you want, but a basic ingredient. We got sugar, we got cream, we got vanilla. Wow, you guys will be the first one that never got this one. Come on, you can do it. Yeah, milk. And then there's really one more ingredient. And since you missed milk, I'll give you the last one because it's the most not salt, as we discussed. If we just stuck this in the freezer, what would happen? Would we get ice cream? Yeah, it would crystallize. It would freeze. Because the heat's going where? If I stuck it in the freezer. Out where? Into the room. Good. Because we obey the laws of thermodynamics. Yeah. We just, heat is the transfer of energy. And so we'll take some of the internal energy of this guy and take it out of it. It goes into the room. So I'm just trying to mix up the sugar from sticking to the bottom. But this would eventually just freeze and be one big chunk. One big milky, creamy ice cube. So the last ingredient that most people overlook is air. We got to fluff it up. Most of air is nitrogen. This is liquid nitrogen. So this is going to take the heat out of this, and it's going to go into this. And what will it do to the liquid? What's that phase called? Change called? Evaporation. Yeah, it's going to boil away. Turn into a gas. What gas? Nitrogen. It's most air. So it fluffs it at the same time as it cools it. That's what we're going to do. I am going to need a volunteer because somebody has to stir and keep it from freezing into a big chunk while the other pours. Deal. You want to pour or stir? Okay. We're going to get safe. You got glasses on, but put the gloves on so it doesn't splash on your hands. And so at first, I pour kind of fast, and she stirs fairly slowly, so it'll splash all over the place. Okay, did I get all the ingredients this time? Milk, cream, sugar. Yeah, I forgot the sugar once. That was a disaster. Okay. Do you want to use the drill or this?
The drill.
Okay. Let's go for it. Now, you can get a little too zesty with this and splash it all over the place. So you'll have to control the speed. Is this a generator or a motor? That's how I'm going to use it. Yeah, a motor, because I'm going to convert electrical energy into motion. So I'm going to send current through the coils in here. They're going to move with respect to a magnet. And that electromagnetic induction, they're going to start spinning. All right. You're welcome to stand up if you want. I find it easier standing on the table using that, but I'll leave it to you. How many made homemade ice cream before? You got to make. How long does it take? Forever. A while. Yeah, I don't think I've ever done it inside of 45 minutes. So, okay, here we go. Yeah, keep it going. Oh, faster. And at the beginning, it doesn't seem like we're doing much, and then all of a sudden, woo, it gets nice and thick. And of course, she can't see what she's doing either. Do you remember the temperature scales? What's room temperature? It's about 20 degrees Celsius, 70 degrees Fahrenheit. What would it be in Kelvin? Let's see. In Celsius, what's 0 degrees Celsius in Kelvin? (273 Kelvin is 0 degrees Celsius. So add 20 to that to get up to room temperature. 293. And Catherine, you'll want to check the sides out so it doesn't get stuck on the sides. You let me know if I need to pause and let you catch up. But I think we're okay thus far. That's more by feel. Who's gaining energy and who's losing energy? We're pulling heat out of this, so it's losing internal energy, and it's gaining it because it's heating up and evaporating. Should we see how we're doing? Oh yeah, we're over halfway. We're getting there. Let it clear so we can see what we're doing. This would be a good soft serve. A little soupy, I think. What do you think, Catherine?
I think so.
Okay, we'll keep it going. Now you'll probably want to go faster and I need to slow down. Oh, that's servable. Let's do it. You just set it right there. All right. So, would you still be willing to help me out, Catherine? All right. We'll dish you out. You can form an orderly line. Here are exam 4s, bubble sheets if you'd like to get them. Over here is some superhero papers. Some people weren't here last class. And we will start scooping. Spoons. Napkins. I better check this one. Last batch I made. That's better.
Good job on the sugar.
That's actually the required amount. I just always do it that way so everybody thinks I'm putting in more than you're supposed to. You can make any ice cream recipe this way. We just use the liquid nitrogen to speed things up. You can even put pineapples in it, Ennis. If you ever try this at home, put the fruit in after you freeze it, because you don't want to get a frozen chunk of banana or pineapple in your mouth. That won't be
We're not
good.
doing work today? What's the deal?
How you doing?
Hey,
I reviewed thermodynamics. Yes.
I was actually coming down here and hoping to see Tabitha because I expected you'd be actually doing a lecture. But since you're here,
Yeah, she was here this morning. She usually comes back.
how hard is it to set up the beating? Wah, 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 this thing.
Not ridiculous.
Could I get it?
I will try my best.
Okay, yeah. Or anything else that's beats. I mean, if there's another one
You
that's
just want to
beats.
see beats?
Yeah,
Hear beats? Oh, I got a much easier way.
Okay. Yeah, so anything, that beats would be great.
Okay.
Oh, they do?
Thanks, Jordan.
Yeah, but I'm talking like something where you just like press the button.
Matt,
Press the button.
come and get it. If you'd like it, yeah. Thanks, Catherine.
Yeah, I can see how it became a mess.
Oh, a third of it just overflowed because she poured the liquid nitrogen in all at once and it just kind of erupted.
Barely walked in on anything you said, but there's supposed to be a grade on it because mine has nothing.
No, that's how it, yeah. Your scores, well, I'll wait to announce all this once they sit down so everybody can hear. I'll use that one. Too much? You're welcome. I hope you like it. Ryan, your test is not in there. Because I wrote what the answers were, and I realized you can't know yet. Oh, you already did? Well, I can give it to you then. I have it in my folder over here. We're getting close. I'm going to pause.
Is this how they do it at like the Sub-Zero?
Yeah, those Sub-Zero ice cream places, yeah, their new thing is to make it with liquid nitrogen, yes. So I haven't been there yet, so I don't know, but it's got to be something like this. It's kind of like Cold Stone. They work on a slab, but that's to keep it cold and so they can form it and it helps chill it down. But the liquid nitrogen is more like in the making, where the Cold Stone is just the forming, you know, after they've already made it. Yeah, the problem, liquid nitrogen is where do you get it and how expensive is it? Well, that all depends. It's not easy to get. And I've never gotten it myself anywhere other than a university, I have to admit. For me at the department, it's on tap and it's like less than $1 a liter. Well, thanks.
Yeah.
Get yours and eat up. A what? If you had to get it, locally, you can try places like agricultural places, because they often use liquid nitrogen to freeze things such as bovine semen, or like Prax Air or Bevco that deliver pop to places, carbonated pop, because they use it to chill, or anybody that transports something that they need to be really cold. They usually use it there and can provide it, but they're usually in the big commercial things, and so you walk in, something, they might look at you funny. So yeah, it's not easy to get. But at the hospital, they would charge like, I don't know, $8, $10 a liter, to burn your ward off. But yeah, here got a deal, and it's less than $1 a liter. The most expensive thing was the cream.
What went wrong on Tuesday? No, you said Monday.
Oh.
Monday. This is Monday.
Long story short, I forgot to put the sugar in. Yeah, I was serving people who were like, oops. I've been doing this hundreds of times, and that was the first time I forgot. But it was my fault. I have an excuse, but it was my fault. So it's going to get runny, but if you need seconds during this, come on down, and I'll let you help yourself. All right, I'll tidy a moment, and we'll move on. Thank you. Thank you, Catherine. Let's see, we probably don't need all of those. Okay. I wanted then also to talk a little, do a couple more demos about electricity. This is fresher in your minds. Should be. I wanted to make a connection for those of you that want to learn more. It'll help review. But it was a big realization for me. Oh yeah, I guess before I get to that, right, somebody asked me, the grade you got on exam day should be on WebAssign, as well as your retake. And again, if you took the retake, I'll average the 2 grades. Friendly reminder that the course evaluation should have been sent to your university email, and I strongly encourage you / remind you to fill that out. That'll help me out a lot. A lot of people forget or like, who cares? Well, I care. So also, I encourage you to check your scores on WebAssign, especially if you are one of those where you turn something in later, or I had to go change a grade. Well, I didn't do it as bulk in the class with everybody else. Make sure I didn't mess up. Like, why do I have a 0 here? You didn't turn anything in. I thought I did. Or, remember I sent you that thingy? Ooh, yeah, I forgot to change that, sorry. So I try really hard, but I mean, it's easier if you check your own and catch me on it. I'm trying to catch it too. That would help. Ryan, come up now. Here you go. There's yours. And thought there was something else. That might have been it. Okay. Back to this. Sources of electric field. What will cause an electric field? What's a source? It's a good review. We get an electric field because there is there you go. An electric charge. Oh, that's what it was too. This reminded me of the question. Obviously, since the exam retake has been due, the solutions are there too with my explanations, so you can see the correct answers and why you missed it or not. So the average on exam 4 day was 66. With those that took it, the average there was like 95 or something. Woohoo. So the combined average went up like 11 percentage points to like 77 or 78. So woohoo! So yes, an electric charge has an electric field. What is a source of a magnetic field? Say that again, I couldn't make it out. Moving electron? Yeah. A moving electric charge. Ran out of room. We'll You know, we'll do like the old days, my daughter, you know. All right. Yeah, electric charge, it's moving. There you go. What else can, though, make an electric field? This was our last chapter stuff. So yeah, we had a charge. If it's just sitting there, we can get an electric field. But we could create electric fields another way. Very good. Changing magnetic field. Where change is the key. Not just a magnetic field, it's got to be changing. Like moving a magnet in and out of the coil. Remember that? And was electromagnetic induction, which means a voltage was induced in the coil, which means current starts moving around, moving charges. You're moving those. You got a current, you got an electric field. Okay. And then there's one more source for a magnetic field. Your clue is, do you see the symmetry? Uh-huh. Changing electric field. Whoop. There you go. So you can have a charge, have an electric field. Now let's move that charge. Hey, you get a magnetic field. Well, why don't we have a changing magnetic field? We get an electric field. You change the electric field, you get a magnetic field. That's a transformer. Remember? You change that electric field, it creates a changing magnetic field, and that induces current over here in the secondary. And my connection that I didn't make when I was a student, has anybody in here heard of Maxwell's equations? Maxwell's equations. Yeah, well, it won't be as cool to you, but that's okay. I want you to know that you go on in physics, there's these 4 equations, Maxwell's equations. They like can sum up all of electromagnetism. They do the connection. Everything we've discussed can be explained with those. And light, ultraviolet, infrared, radio waves, all of those are electromagnetic waves. And it explains all of those. He was the first guy to realize what light really was. It was an oscillating magnetic and electric field. They kind of self-induced each other, so to speak. They went together. Well, his 4 equations, the math looks scary. I won't write them down because we haven't even done it. But they're short little equations, and all they mean is exactly this. You know the concepts to understand light. We didn't get to it, but one says, hey, you have a charge, there's going to be an electric field. The more charge you have, the stronger the electric field. If it's moving, you're going to get a magnetic field. And everything I just said, that's all his equations mean conceptually. They just allow you to figure it out mathematically and solve anything you want with electromagnetism. It's pretty impressive. I thought that was cool. I thought of wearing my t-shirt, but I didn't think it was probably over the top. It's got his equations, and then it says, and God said, let there be light. But so that goes to, let me show you what an electromagnetic wave looks like. Oh, it just shut down. Well, we'll give it a moment, and then I'll show you. Let me turn it, while this is coming up, what you guys thought of any questions? No? Well, that'll make life easier. Okay. Raise your hand if you think of something. All right, so just to show you, we can represent an electromagnetic wave. Well, the only thing that's different between like light and radio waves and microwaves is the wavelength. See these bumps? They go up and down, a sine wave? It's the spacing, how long or short they are. The shorter they are, the faster they vibrate, and the more energy they have. The longer they are, the slower they vibrate, and the less energy they have. And that corresponds to any waves, sound waves, radiation waves that we talked about. The sun has a higher energy, so it puts out shorter waves than the earth. Still has a temperature, remember that? So it radiates, but they'd be longer waves. But a wave's a wave, and an electromagnetic wave has an electric field, let's call it the yellow, and a magnetic field. And they are oscillating and changing in time, spatially. I mean, it helps picture like a wave going up and down, but it's like the electric field at this point, as it passes by, gets stronger and stronger. Oh, then decreases, goes through zero, changes direction, gets stronger and stronger this way, comes back. But it's constantly changing right there, thus inducing and creating electric and magnetic fields. It's kind of like it's self-reinforcing in a way. It's the best I can explain it. But there's at least a visual you can represent, so you could see and picture how these concepts can relate to what light really is. So as one changes, it helps the other, but it's changing, so it helps the other. And they propagate through space at the speed of light. In a vacuum. They all go the same speed. Light is my all-time favorite subject in physics, I have to admit. But there we go. So, let's review some more. Any questions? Oh, good, we got a question.
So the electric wave and the magnetic wave are, as you said, self-propagating. How far would they have to go to eventually become without energy?
Yeah, I have to qualify myself first, I have to admit. Self-propagating is to help understand, because one induces the other and the other induces that, but that sounds like a perpetual motion machine to me. So it's not, but yeah, if I turn on a laser and do a little pulse, and it sends it out, that would go forever because of inertia. And it would do that unless something interacts with it. Thus, air particles could scatter it, and thus it might not reach very far. But out in space, you do a laser beam, that should just keep going until something can dissipate it, reflect it, redirect it, scatter it, absorb it. It should go forever.
So it would go there. So it's like a perfect transformer?
Like a perfect transformer. Never thought of it that way, but in a sense, yeah. They're definitely the most efficient transfer back and forth. Yeah. Okay, now you guys are all feeling smart, right, with electricity. So I don't go home and try this, because if you touch the wrong part, you could electrocute yourself. So let's sacrifice this pickle instead. You remember the difference in voltage between the hot side and the neutral side? The two prongs, not the round ground one, but the two prongs. That's what comes out of your outlet. The difference is going to be 120 volts. So that means, yeah, there's a difference of voltage. So if you provided a path, it'll give the push. And push what along? Charges. And where do those charges come from? The circuit. There's charges in this pickle. So it's going to set up an electric field because we've separated charges. That provides the voltage. That electric field exerts forces on those charges and they start moving, drifting along. I have to admit the most missed question on the test was what's the speed, the drift speed of the electrons. It's not the speed of light. There's a whole section in the text on it. They just drift along at a snail's pace. The electric field, as soon as you close the switch, is established at nearly the speed of light. But the actual charges do not zip around at the speed of light. They're kind of randomly moving. There's a picture in the book. They just kind of drift. Real slow, real slow. But they all start doing that at the same time because as soon as you flip the switch, they all feel it. And and the source they're already there in the pickle. So, I have my GFCI circuit here, so in case I touch something I'm not supposed to, it should shut off. Don't let that be you. See, it's smoke steaming too. What's happening is, well, everything we just said, but there's resistance. And so it heats up. And it vaporizes the water next to the electrode, makes it kind of dry, worse conductor. So it starts arcing and sparking. And that breaks down the salt in the pickle. And the sodium starts to glow. That's the yellow that you see. That would be you. I don't think we'd glow, but it would burn your flesh. Get extremely hot and kill tissue cells. Besides the fact all the current's flowing through you, that wouldn't be good either. But
So exactly what's producing the resistance?
those charges are in the pickle, and they go, ooh, there's an electric field now. Somebody close the switch. Somebody's trying to push me one way. Well, what do they run into? All their neighbor charges and molecules. And so they try to move at the speed of light, but dang it, they ran into this guy. And he runs into that. That's the resistance. And that resistance converts a lot of this electrical energy to heat. So yeah, it heats up. And then we go back to thermodynamics. We have a phase change. Well, great, that changes the conductivity of that region, which changes the resistance and the amount of current that flows. It ends up sparking, and so on and so forth. But did that help, Mary? Okay. Now, what else is cool about this demonstration? It helps us review some more electromagnetic induction. The way a GFCI, ground fault interruptive circuit, what it does, the basics of it, most of them, they have a coil of wire. And they send the hot wire through it and the neutral wire through it. But the current in those two are going in opposite directions. So if you have current flowing through a wire, what else is established? A magnetic field. Yeah. And that changing magnetic field, because it's AC, so it's alternating, but they alternate, means it's a changing magnetic field. The changing magnetic field does what to the coil? Electromagnetic induction induces a voltage which pushes charges around in the coil. Well, the neutral wire does the same thing, but in the other direction, because it's always changing oppositely, opposing. And so it does the same thing, but it sets up a current in the coil trying to go the other way. So the net result, if everything is happy, current comes out to your device, comes back. The same current that goes out comes back. If they're the same, there's a no net effect in that coil. Are you with me? And we're happy. So what if you grab here where you're not supposed to? Some of the current's going to leak off through you. You kind of made it a parallel circuit through you. All of the current won't return back. There'll be a difference. Now there is a net current in there, and it senses that change and shuts it off. So in theory, you don't die. That's how those work, and you know how now. It's because current flowing through a wire creates a magnetic field. That current's changing, so is the magnetic field. That changing magnetic field induces a current in a little coil. But the other wire's doing the same thing in the opposite direction, so they cancel. If it notices any difference in either of those wires, the hot or the neutral, now there is a net current in that coil, and it sends to a circuit that shuts it off. Clever. Those switches in your bathroom, you know, the one with a little plug, and you're like, dang it, why does it keep turning off? And you have to reset it. That's a GFCI circuit. And then we had many requests to turn this on again. So walk me through it. How does this work? 120 volts over here. Then what happens? It goes into these guys. Steps up what? The voltage. What stays the same? The watts, which is the power. These are transformers. This one steps up the voltage to about 8,000 volts. So are there more turns on the primary or the secondary? Right. If there's more turns on the secondary, then the voltage goes up. Power ideally stays the same. So 8,000 volts. That's connected to the white cylinder, which is a capacitor. What happens? Good, it stores charge as well as half credit. Wattage, power, energy. It stores energy. Because it takes work to separate the charges in the capacitor, to store them and separate. So you just put energy into it. So now it's stored in its electric field, ready to release. Electric potential energy. Energy per charge is voltage. So we can get this up to 8,000 volts. Actually, it can go up to 10,000, but we're only giving it 8,000. Then they are connected to a circuit with a spark gap in the back that's not connected. What happens if the difference in voltage between these two sides gets large enough? It arcs and jumps, breaks down the air and makes it conductive so it can make it across. Dumps all that energy into this coil, and this is essentially another transformer. Is it stepping up or down? Primary, secondary. Big turn ratio. So this steps it up to at least 500,000 volts. I don't remember how many there are. And it stores charge up here until it breaks down the air and starts sparking. But how does it induce voltage in here? Electromagnetic induction. What's flowing in here? Current, and it's changing. So a changing magnetic field causes a voltage in here, which pushes its charges around. So let's turn her on again. Where'd it go? There it is. It's cooler with the lights out, isn't it? I'll just do the front lights. So turn it on, and on again. Triple safety. The length of the sparks give us an idea, it's a rough estimate, of the voltage. Remember we did that with the Van de Graaff generator? We said, oh, if the spark is this far, because another way to look at electric field is volts per meter. Volts per meter. And air broke down at, 30,000 volts per centimeter. So, I won't bore you, but we had, with a Van de Graaff, it was like 4 or 5 inches, and that equated to about 400,000 volts. How many inches are these? Over 12, some of them. So if 5 inches was 400,000, 10 inches is... Anyway, it gives you a rough idea. Things change with higher frequency stuff, but whatever. We can at least use it as a review. I made a little doodah up top. And it has sharp points. What happens at a sharp point to an electric field? Do you remember that? Yeah, concentrated higher there. Remember when I connected one of these little things to the Van de Graaff? What did it start to do? It started to spin. So it's going to like discharge there, but then it's a collision in reverse. It's like a rocket throwing exhaust gases out the back end. If the rocket exerts a force on the gases exert a force back on the rocket. So same thing here. It'll recoil and feel an equal but opposite push, and this thing can stay spinning. Let's see. Except there's too much friction. Notice sparks only came off where the sharp points were at for everything we just explained, because it's easier there. That's where it wants to discharge. It didn't spark off of this when that's attached. And some of you might have been noticing these are still lighting up over there. That's because this is alternating. The current flows through one way or another. This is emitting electromagnetic radiation. These charges are changing electric and magnetic fields going on all over the place here. So they actually create an electromagnetic wave that radiates out. And it contains energy. Just it's in a different form. And it comes over to here and it starts making the charges inside the tube, the gas in there, to oscillate and light up. This establishes an electric field because there's a whole lot of charge here and less over here. And what's that want to make these charges do? Move. And so yeah, you can get this to light up. This is what Nikola Tesla, how he wanted to power the United States. Wirelessly. You know why? One main reason it never worked? Why we don't do this now? What's that? Money. Yeah, money. How do you charge someone? It's like free energy. You just stick the light bulb up in there. How do you regulate it? I mean, that was a big issue. So, now we have Wi-Fi and Bluetooth and cell phones all over the place. They use electromagnetic waves, which are just changing electric and magnetic fields, which can induce currents in an antenna or your little signal thing, and then we can convert that back to electrical energy and drive what you need. And they oscillate at certain frequencies. That's how you can tune into the station you want, or your cell phone or whatever. Questions about the Tesla coil? Any killer questions, things that have been confusing you? The test, or the final, I won't see you guys for a week. It's next Wednesday, same time, same bat channel. We're that close. Yeah, I'd rather answer your questions if you have any. So, how many questions? I haven't decided. I'm leaning towards 50. More than 30, probably less than 60. Does 50 sound reasonable to you? I figure most of you are done inside of an hour with the 30. I mean, I don't see any reason to, just for the heck of it, double it, but I don't know. I haven't decided. Well, thank you very much, class. Been a pleasure.